All right, everybody, welcome back for section 3 of our new cybercrime course. And today we are going to be talking about hardware. What makes a computer work? What are the different pieces you need? What's going on in that little box thing you got? Whether it's a desktop, a laptop, or um, really any digital device is going to have essentially these same pieces, just in slightly different form. Now, the piece we're all kind of probably most familiar with is the case. And this is usually just, a big plastic or metal box that houses all the other components. Usually has some features to help provide cooling, but not a lot of digital evidence to be found here. Obviously, we're going to be looking at this for things like fingerprints, um, but not a lot of actual data stored anywhere on this actual piece. Okay, the power supply. This is usually a little boxy boy that sits in the case, and on the outside of the case there will be a place to plug in the actual power connection, and then it has a whole bunch of other little power cords that come off of it on the inside of the case in order to plug into each of the individual pieces of the computer and provide them each with their own power. Again, not a lot of digital evidence to be found here, but it's important to understand that these pieces need to be plugged in the proper place. And luckily, modern power supplies, each one of the different cords has a different kind of connection that will only fit where it's supposed to go, so you don't have to worry too much about plugging things into the wrong place. Disk drives, these are kind of vanishing over time just because we're increasingly moving to a non-physical media based computer system, especially the floppy drives as pictured there at the bottom. But you still find some computers with DVD drives or Blu-ray drives, and again, these don't have a lot of evidence on them other than the fact that if there is a disk inside one, you want to make sure and seize that disk and examine that disk. Now, the video card, this is usually what the monitor plugs into at the back of the computer. This is essentially its own little mini computer with its own processor and its own RAM, which we'll talk about here in a minute. But it's entirely in charge of generating graphics. A lot of kind of more normal lower end computers will have this piece built into the motherboard, which again we'll talk about here in a moment. But especially people who play video games like to have a separate video card for faster and better graphics processing. Sometimes higher end PCs will have two of these or even three. But if you find a whole bunch of video cards, chances are that person was mining cryptocurrency, probably Bitcoin, because the graphical processor units are more efficient at mining cryptocurrencies usually than an actual CPU. So if you find a whole bunch of these and they're all hooked up, chances are they're not using them for actual video processing. They're using them to obtain cryptocurrency. Now, on the motherboard, this is kind of the backbone of the electronic part of the computer. So at its core, it's really just, a sheet of circuit board with a bunch of sockets and slots built into it that you plug all of the other pieces into. Now, and then it has connections between those sockets and slot to allow them to all kind of communicate with each other. In the modern day, motherboards are going to have more things than that built into it. Most motherboards today come with built-in and already kind of permanently attached to the board things like Ethernet or Wi-Fi. So you can either plug in a cord into the back of the computer in the case of Ethernet, or the Wi-Fi can connect to a wireless network point somewhere within range. Most of the time these days, those are built into the motherboard. All the hardware and for sound processing and plugging in your speakers is usually built into the motherboard. Video If you don't have a specialized video card, as we talked about a slide or two ago, the video processing hardware will be found here. And then I/O, which stands for input output, i.e., this is where your keyboard and mouse are going to plug in, and it's going to have all the hardware for running all that basic, input output hardware and externals that you plug in. And then, of course, there's the BIOS. And the BIOS is actually an incredibly simple, essentially an operating system just for kind of when you first turn the computer on, before you've loaded all of your Windows or Mac OS or Linux software. The BIOS is what kind of the software required for the computer to kind of turn itself on and say, oh, look at this. I'm a computer. I have this kind of drives attached, and I have this kind of keyboard and mouse. And oh, my user has said that I'm supposed to run this Windows program located on this drive. So I'll load this Windows program for them. And then once that process is over, then you can start using your computer as a normal user. Now, the processor, this is kind of the brain of your computer. This is the thing that takes in ones and zeros, does math on them, and then spits out an answer. I mean, at its core, all it's really doing is taking in sequences of ones and zeros, adding or subtracting them, some cases, some minorly more complicated processes than that, and then spitting out an answer. And this is what the entirety of modern computing is built on. Taking in ones and zeros, doing some simple math, spitting out an answer. And by making that more and more and more complicated, we have YouTube and video games and Zoom conferences and everything else your computer does, when it boils down to it, is just your processor doing that mathematical operation millions or even billions of times every second. And interestingly, these processors usually are not limited by kind of how theoretically fast they can do math. They're limited by heat. So your processor in your computer at home right now can probably run 2, 3, 5, 10 times as fast as it's running right now. The problem is that would generate so much heat that it would melt the chip. So there are lots of pieces of the inside of a computer that are devoted entirely to getting rid of that heat generated by the processor and a few of the other components. Pictured there at the top is a heat sink, which is just a piece of metal that sits directly on top of the processor to draw heat away from the chip and up into those thin little metal veins. And then it usually has a fan on top of that to blow cool air onto those metal veins to cool them down, to help radiate that heat out and convect that heat out away from the processor. And then usually your case will have at least one or two other fans to try to change out the air on the inside of your computer, all in an effort to keep the temperature down so this processor can run as fast as it's kind of designed to kind of hope to. But again, if you get a really nice fancy say water-cooled or glycerin-cooled rig on the inside of your computer, you can force a processor to run much faster than it's kind of rated for. Now, if a processor is going to take in ones and zeros, do math on them, and spit out an answer, it needs a place to get those ones and zeros from, and then a place to store those answers in. And that's RAM, which stands for Random Access Memory. Now, memory is just the place where these ones and zeros get to sit and stay, and then the processor says, oh, I need the ones and zeros in slot number 15, and I'm going to add those to the ones and zeros in slot number 12, and then I'm going to store the answer in slot number 42, whatever, picking random numbers there. So RAM is just a repository for all the ones and zeros for the programs you are currently working on, right? So at my computer right now, as I'm recording this, I have the Windows software loaded into RAM so it can be used by the processor, and thus me as the user can run Windows. I also have the software for recording this lecture. I also have the software for PowerPoint. All those ones and zeros that comprise those programs have to be in RAM so that the processor can kind of, take the ones and zeros that the instructions tell them to take, do that math, spit out the answer, and then the answers can be used to, run my webcam here and display this picture on the screen and all that stuff. All of that is just kind of the mathematical output of that processor that was put into the RAM and then used by those other pieces, like my monitor, like my webcam, like my speakers, all those things. Now, at its simplest form, that's how a computer works. You plug in all those pieces together, and then they work together to do math, to run programs, to allow the user to do any one of essentially an infinite number of things. And back when I was young, there were far, far, far more options for each one of these. So this display here is a little bit out of date at this point. It's a lot simpler now, but it still kind of illustrates that there's different kinds of RAM. There's different kinds of CPUs. There's different kinds of video cards. And so one of the important things if you're going to build your own computer is to make sure that your motherboard slots is designed for the kind of CPU you want to buy. Because if you buy the CPU with one socket type, but your motherboard has a different socket type, they're not going to work. And luckily, modern computing has definitely reached the point where if it fits, it will work. If it's not supposed to work, it won't fit. They're going to, if a certain CPU socket, if your CPU can fit in that socket, your motherboard is designed to work with that CPU. So as long as it fits, it should work. But you need to make sure that the slot for your RAM on your motherboard is the same as the kind of RAM you're buying. So again, there's far fewer than this now, usually in kind of major circulation. But it is a very complicated process, relatively, in that you can't just buy any old RAM and any old CPU and any old video card and expect them to work with any motherboard. Now, at its simplest, all we really need for a computer to run is that RAM and that processor, right? And then, of course, some basic input-output things. And that's essentially how the really, really old school, 1940s, 1950s computers worked. They were essentially, the equivalent of just memory and a processor. But the problem with RAM is that the ones and zeros stored there are what's referred to as volatile. And that volatile means, in this case at least, easily lost, easily destroyed. Because RAM stores ones and zeros entirely electronically. So it's the electricity running through that RAM that allows those ones and zeros to be stored. And if electricity is shut off, all the ones and zeros in that RAM disappear. They're gone, like they never existed, because they're entirely 100% dependent on electricity running through them, right? So again, those early computers, every time you turned it on, you had to kind of manually input all of the ones and zeros for the program you wanted to run, then the ones and zeros for the data you wanted to run it on, and it took hours and hours and hours. And the vast majority of time spent with those computers was not on actually running programs. It was on inputting ones and zeros, then getting the ones and zeros out for the answer, and doing maintenance and replacing pieces. So they had very small percentage of their time was actually used with running programs. So relatively quickly, they realized they needed a way to store data permanently. So if the power goes out, or the machine gets turned off for maintenance or for any other reason, power loss, whatever, you could easily re-input programs and data and all those things without having to manually put it in every time. And that has, it started with punch cards, and then moved into other, tape, like, old audio cassette tapes, and has gone through lots of different ways of storing that data permanently. But the vast majority of computers these days have some kind of hard drive or hard disk, and that's how they permanently store data. But we're going to cover hard drives and permanent data storage in the next subsection. Thank you for watching.